These heaps are the unhappy legacy of an industry that contributed every bit as much to Britain's industrial prosperity in the 19th century as did the more familiar textile industry. They were left by the pioneer chemical manufacturers. Now, with them in view, it's a bit difficult to say that the chemical industry, or the alkali industry in particular, is rather like an iceberg. But what I mean is this: the industry produces a great many materials that we have no direct contact with. They're the raw materials of other industries.
Take synthetic alkali, for example. Over 2 million tons are packed and distributed every year in Britain. Basically, the term alkali covers various forms of soda and potash, but we'll concentrate on the most common type, sodium carbonate. In the past, it was obtained from natural sources, but now it's manufactured from other chemicals. Apart from perhaps washing soda, we see little of it as such. The reason is that soda is used as a raw material for other industries. About a third of the output goes into the manufacture of other chemicals, but the remainder is used in processes that have seen enormous expansion during the last 200 years. At the end of the 18th century, Britain was in the first stages of the Industrial Revolution. Textile manufacturers used soda as part of the bleaching process. And they also needed soap, which is itself made from soda. Rising standards of living were calling for more glass, which is also made from soda. But there was virtually no alkali industry to meet this demand.
So what we're going to do in this program is to try and give you some idea of the economic and political factors that influence the rise of the alkali industry, and also to give you some idea of the time scale involved.
Traditionally, alkali had been obtained by burning wood. As the forests were severely cut back, this source gave rise to barilla, the ash of certain Mediterranean plants. But due to the wars, imported supplies couldn't be relied on, so one alternative was to use seaweed. When burnt, this gives a product similar to barilla. But supplies remained inadequate, and a synthetic soda-making process was sought. The most likely starting point was common salt, sodium chloride, which was produced either from mines or by evaporating seawater in pans by the sea. In a nutshell, the problem was to detach chlorine and substitute carbonate to give sodium carbonate or soda. The 1780s saw a rash of applications for patents for the use of salt as a raw material, if possible in a process that avoided the heavy tax on salt. In Edinburgh, for example, the professor of chemistry, Dr. Joseph Black, one of the most distinguished chemists in Europe, teamed up with James Watt of engine fame.
The processes that were being tried out in this country by these pioneers were in fact almost on occasion indistinguishable from the process that was ultimately imported from France and became the mainstay of the British chemical industry until quite late in the 19th century. Other pioneers tried other methods, but they seemed to have difficulties. What I suppose happened was that they had a process that would work all right in the lab, but they couldn't convert it to a full-scale industrial process.
The search for a synthetic alkali was also going on in France. There, the Academy of Sciences offered a substantial money prize for a successful process. But though a Frenchman finally discovered the process, which became world famous, many thought the English had beaten them to it. In 1849, in a paper describing the many uses of common salt, the distinguished scientist Fourcroy wrote,
"One feels today the need for a more important use than all these. the extraction of soda, which every day becomes more and more rare, and which is necessary for all arts. Many persons possess this secret in England and withdraw on a large scale soda from the salt of the sea.
A patent had been granted to one Nicholas Leblanc, surgeon to the Duke of Orleans, in 1774. In 1790, he was awarded the Academy's Prize, and a year later established a factory near Paris. But times were far from peaceful. For Europe's greatest chemist, Lavoisier, the revolution ended everything. Leblanc survived, but lost his factory and killed himself in a pauper asylum. However, his process continued, and in the war with Spain, when supplies of natural soda were cut off, over 17,000 tons were made. The first stage of the Leblanc process is to put salt into a pot like this and pour sulfuric acid over it. Dangerous acid gas is given off. The remaining mixture is heated in the furnace behind the pot and raked out as a solid called salt cake. This salt cake then goes on to the second, or black ash stage. There's no Leblanc now working in Britain, but this record of an old plant operating in a similar way has survived. The wagon is positioned over a grating which allows the contents to be discharged into a furnace. In addition to the salt cake, coke and limestone are also fed into the furnace. The furnace is made so that it revolves and mixes up the contents as they react together. When the reaction is completed, the furnace is tapped. But before this can be done, a workman must break through the crust that has formed on the inside of the furnace. Pouring can now start, down into the waiting bogies. Because of the mixture produced, the furnace came to be known as the Black Ash Revolver. The Leblanc process needed a lot of manual labor. Even at the pouring stage, an operator had to tug the bogies forward before they overflowed. The process wasn't without its own folklore. The black ash contained waste gases which gradually burned away, and it was said that the mixture had the appearance of pudding with candles on it. The cooled mixture is broken up before being taken to the next stage, where the soda is dissolved out by water, leaving solid waste to be dumped on the tips we saw at the start of the program. This is the crystalline form of soda, the purest Leblanc alkali. It wasn't very pure, but it was acceptable, even if this was at the sacrifice of the men who worked under appalling conditions to produce it. So where were the first plants, and what effect did constraints like taxes on salt have? In Britain, the first Leblanc works were around the Tyne. There were two main reasons for this. The alkali needs of the long-established soap and glass makers in the area, and the supply of raw materials. Low-quality coal was used to evaporate seawater on such a scale that smoke could be seen 40 miles away, so there was plenty of salt available. The first successful alkali pioneers were the Losh brothers, who, in partnership with the Earl of Dundonald, were producing soda by the Leblanc process as early as 1800. They dodged the salt tax by getting their salt from a brine spring, which was exempt from duty. It was only when the severe tax was removed in 1823 that alkali production by the Leblanc process spread to Liverpool, where James Muspratt added it to an existing sulfuric acid works to supply the needs of the Lancashire textile industry. Unfortunately, Tyneside's massive pollution came with the process. This took two forms: waste tips and the acid gas produced at the start of the process when the sulfuric acid is poured onto the salt.
Both sides of the Tyne, I remember, were covered with bonny green fields, but now there is nought but big furnaces, down from Newcastle to Shields. And what with their sulphur and brimstone, their vapour, their smoke and their steam, the grass is all gone and the farmers can nowhere get butter or cream.
Charles Tennant, a Glasgow bleacher and chemical manufacturer, improved things a bit. He was making bleaching powder from chlorine to supply the rising needs of the textile industry. And fortunately, there was a simple way of getting the chlorine he required from the hydrochloric acid gas produced by the Leblanc process. He called his bleaching powder comparatively innocuous, but perhaps those making and packing it didn't feel quite the same way.
There was a cat used to come worriting round here, stealing our dinners and such like, and I wanted to get shut of him. So I collared him one day and took him into the packing chamber and gave him a sniff. He was green in a second.
And a cat has 9 lives. A man only 1.
But for a long time, the demand for bleach couldn't absorb all the surplus Leblanc hydrochloric acid, and serious pollution continued. The belief that if you built tall enough chimney stacks, you could get rid of it into the atmosphere led to monster stacks becoming a characteristic of the chemical manufacturer's landscape. In the upper house, Lord Derby succeeded in having a select committee set up. The alkali manufacturers, sensing stormy times ahead, banded together in 1862. And it was this that avoided really crippling legislation when the Alkali Act, the first anti-pollution legislation in the world, was passed in 1863. The essence of the act said this: if your process produces hydrochloric acid gas, you've got to absorb 95% of it. In other words, the recovery of byproducts became a legal necessity. And it's from the years immediately following the Alkali Act that the most effective recovery processes date.
The Alkali Act was the first of many acts to protect the environment, but in some ways it was rather two-edged. Before, the alkali manufacturers had passed thousands of tons of hydrochloric acid into the atmosphere. They now had to absorb it. It became a solution. What had they to do with it? Well, they passed it, sometimes when nobody was looking, into rivers and canals like this, so causing pollution in another direction.
Given this situation, a technically more sophisticated process had a good chance of success. In 1830, A.J. Fresnel had observed this. He started with a solution of common salt, or brine, and passed ammonia through it. This at first is immediately absorbed. The bubbles never reach the top of the tube. But several minutes later, the rate of absorption is greatly reduced. The bubbles of gas are now rising up the tube, and finally, the brine is saturated with ammonia.
And in 1873, Winnington Hall, near Northwich in Cheshire. They built their works in the grounds, lived on the site, and Mond, who was
put the process into large-scale operation and granted a license to a German chemist, Ludwig Mond, who had already emigrated to Britain. Mond looked round for a likely site, and just as important, a likely partner, and found one in John Brunner, who already had commercial experience in Lancashire.
And this is where they began in 1873, Winnington Hall near Northwich in Cheshire. They built their works in the grounds, lived on the site, and Mond, who was the chemist, virtually slept on the plant. Success came quickly, but not without a lot of hard work. In 4 years, they had doubled their output in the face of opposition from the established Leblanc manufacturers. And by their success, they changed the whole face of the British chemical industry. The plant today is very much as it was designed by Mond. It's been renewed, of course, and there is vastly more of it.
To provide the carbon dioxide for the Solvay process, you need limestone. You also need coke. These are mixed together in the required proportions and carried to the top of a row of kilns. The limestone is readily available from quarries 30 miles away at Buxton in Derbyshire. The coke is also obtained from local sources. Up on top of the building, the mixture of raw materials supplied to each kiln is carefully regulated. This is one of the few stages in the Solvay process, unlike the Leblanc, where an operator is required physically to manipulate machinery. As they pass down the kilns, limestone and coke burn to produce carbon dioxide and, apart from some carbon monoxide, the only other main product is lime. Lime is very important further on in the process, but we'll come back to that later. The carbon dioxide is then blown into the bottom of a large tower called a Solvay tower. This is the test tube of the experiment, magnified so that it's now 80 feet high. It's fed with brine obtained from nearby brine fields, which has previously been saturated with ammonia from an ammonia still. As in the experiment, it's necessary to cool the solution because of the heat generated in dissolving the ammonia in the brine. This is done in a series of folded tubes. In modern plants, these heat exchangers are replaced by more advanced designs, but the old-style units are still sometimes used at Winnington. Here, cooling water is trickling over the tubes containing the brine, and the cooled solution returned for the ammoniation process to be completed. It takes about 2 hours to produce the precipitate, and much of the efficiency of the process depends on how well the temperatures of the solution in different parts of the Solvay tower are controlled. The slurry which comes out of the tower is the bicarbonate precipitate suspended in a solution of ammonium chloride. The precipitate has to be recovered from the solution, and this is done by a special filter called the Brunner-Mond filter. It's a drum, on the outside of which is cotton mesh. The solution is sucked through this mesh, leaving the precipitate on the outside. And as the drum rotates, a knife edge scrapes it off. The soda is obtained by heating this bicarbonate in large roasters. And at this stage, half the carbon dioxide originally used is regenerated and piped back to the Solvay tower. The solid product is pure when compared with the product from the Leblanc process, and it can be packed directly in bags or stored in silos. But the key to the process lies in the recovery of the ammonia. This depends on the lime formed in the kiln at the same time as the carbon dioxide. The lime is slaked, that's to say, mixed with water in these large revolvers. It's then a simple matter to regenerate the ammonia. All that is necessary is to react the slaked lime with the ammonia solution left after the Brunner-Mond filter. Over 90% of the ammonia required for the process is regenerated during this reaction. The only other products remaining are fairly harmless salts, which are later processed in separators. And the final outcome, a cool, clear liquor, is discharged to waste into the nearby River Weaver.
You might think that the Solvay process would have swept away the older Leblanc process in a matter of years. It produced a pure product. You could recycle some of the reagents used in the reaction, and it wasn't beset with the economic problems of having to dump large quantities of valuable waste. But the Leblanc manufacturers fought back. They became more scientific. They appointed scientists of standing. They improved their recovery processes, and this gave them an extended lease of life. However, they had to rationalize, and the rival Leblanc people came together in 1890 to form the United Alkali Company. Then, another rationalization took place. Brunner-Mond, who had been working the Solvay, and the United Alkali Company were joined by the British Dystars Corporation and the Nobel Explosive Corporation to form one of the largest chemical complexes in the world, Imperial Chemical Industries. So while Imperial Chemical Industries as such is only about 50 years old, its origins go back to the late years of the 18th century, or depending on the sort of yardstick you use, even beyond.